about GammaH2AX before, and I guess you are familiar in some way or another with GammaH2AX, I guess. So some of the concepts I will repeat a little bit, but I want to use GammaH2AX to give a kind of hint what we were talking yesterday in the previous day. Remember we were talking about physics and biology? In something, sometimes it's very difficult to comprehend that, in the sense that we are talking about a track, we're talking about a photon, a charged particle, DNA damage, and we know that something happened in between. But it's very difficult to see at the same time or close to real time with each other. So we have an evidence that the physics have an effect on the biology. And this is really interesting, very cool for me. So what we'll talk today is the GammaH2AX as a probe, okay, to investigate some basic DNA damage processes, but also have other implications in terms of physiology and other areas beyond the DNA damage. They have a lot to do with risk assessment. At the end of the day, GammaH2AX is considered one of the latest biomarkers of risk if we can measure double-strand breaks. It is a good representative double-strand break where we can do some assumptions and do some risk analysis based on what we can do, or what a human being receive in an accident, nuclear accident, or any other incident that can receive some kind of radiation, and maybe we can probe for some DNA damage in certain point after the radiation. Kind of tricky, but we will talk about a little bit. So I will start with this this cover, the first slide, and you can see some interesting images. What you can say about these images? Something called your attention, these images. We assume that it's GammaH2AX, right? Okay. So, I'm sorry? How do you know that? Really? Well, let's assume that's the case, okay? So do you think that maybe those cells, assuming 3 different cells, because this is a nuclear, right? The 3 different cells. We have a different radiation dose, similar radiation dose. What do you think? Yeah, you're somewhere right.
Yeah, this is like low LAT radiation, like gamma radiation.
Mm-hmm.
So we have like
the left, the middle of the
right.
Okay. Okay.
And then these like high LAT radiation, so giving like a narrow track of the ionization. So a lot of ionizations along like small area.
But we assume that this image is a kind of trick, right? In order to obtain these images with a track, and you can see a track inside the nuclei, you need to do something just special. Exactly. That's the only way that you can see tracks, right? But even if you have 2 cells, okay, irradiated horizontally, in this case, this is the case, you can see differences. You can see the difference between these 2, obviously the number of tracks. Do you see any difference in the tracks? This track, for example, versus this one. Is any different? So will be a different on. Exactly. In LET, some kind of different LET. You agree with that? Why? Why do you think it will be a different LET? When you say dense and intensity, what do you exactly mean?
It's more green.
Let's look at scientific words. In physics world. Ionization events. Okay? So, you know, every intensity over there, they have an event, an intensity, ionization events. that depend on the LET, the energy, the velocity of the particle, you have different density of those events. That's a typical LET. Okay? All right. Let's see. Okay, this is a kind of the introduction just to, it's a blah, blah, blah garbage in the sense that what are we talking about that? In principle, when we talk about GammaH2AX, so we assume that we measure double strand breaks, correct? Right? Are you sure about this? Wait a minute. You are measuring double strand break here?
Repair.
What do you say?
Repair.
Repair. So, do you know? I don't know. Maybe there is some way just to, if you have a double strand break in the molecule, you need, maybe you can tax the end of the break. But I don't know nothing about that. I don't know any molecule or type that can do that. But maybe what I can do is a trick. Do the repair protein, tag it, and we can see the recruitment of proteins where actual repair happens. So it's an indirect way to measure or visualize tracks. Okay, blah, 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 blah. We can, different ways to do that. But I want to show you this first. And this is what we're talking about. These are very simple schematics. You have the usual DNA. You have the a track hitting the molecule, double strand breaks, and you have repair proteins that go in and actually accumulate over there and produce focus. That's basically like that. It looks very simple, right? But it's a little more complex. So, this kind of, I will not explain all of them, don't worry about that. But I think what is important to say that is, there's many ways to produce double strand breaks or single strand breaks. There's double strand breaks. Many agents, chemical, radiation, blah, 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 blah. And there's some kind of common pathway that will activate this protein for the repair. It's basically a phosphorylation of this protein, correct? And there are other proteins related to different pathways and from the loop that this protein needs to go through to auto-regulate. So when we're talking about GammaH2AX, sometimes it's good to think about it. There's all these proteins around. They are related to that, to the repair process. That's the reason sometimes we use more than one protein to localize the repair process. And it's good to use some of the, because Charles showed, there are several markers related to the GammaH2AX that give us a little more information about what's going on here. One of typical is 53 VPI, or 1. So there's a lot of people using co-localization of GammaH2AX and this marker and other markers, just to understand what is different pathways and also cell cycle relationship with this, and we'll talk about a little later. But this is the big monster, okay? And basically it's a phosphorylation of protein, GammaH2AX. That will be helpful to track some double strand breaks. And this is kind of list, you know, the agents that can produce DNA damage, and it can be probed by GammaH2AX. So you can see it's a long list of different compounds, ionization radiation, of course, and you have certain patterns that you can distinguish. The local points on foci and focus, or a diffuse way. So there is some studies that you can relate and read about what are the relationship between the chemicals, physical agents, and how the GammaH2AX is expressed. Yes? Yes, yes. Thank you, Steve. Also, as Charles said, it's very cell-dependent. And also now we can talk about tissue-dependent. Okay? We are using this probe not only for monolayers of cell, for any kind of cells, and also tissue that one of you, Joe, is very familiar with, as I think some of you too. But there is increased interest in pro-DNA damage in intact tissues, not only in vivo but in vitro too. So, Joe, you have experience that you tried before with the skin, and GammaH2AX was super. Yeah. I have a little experience, kind of difficult with brain. So, and there's a kind of history behind that. But you know, this is a kind of collage of images representing different kind of cell types. For example, in panel A, you have a human peripheral blood, a mononuclear cell, 30 minutes after 1 gray ionization radiation. This is the kind of typical of that. Colors, you know, change depending on your tag, depending on your antibody, what contrast in your nucleus. So you can see a lot of colors. But the main thing is to see what is the distribution of this marker as a foci, as a focus, diffuse. And you can see there's all these kind of combinations, and you can read here what is what, okay? But what really attracted me is this. You know, I mentioned to you, or several of you, that I'm a space buff. So the reason I'm here is because I like space. And my whole career was trying to understand what is the effect of space radiation on the central nervous system. And one of the first images that I got, physics, is this, a photographic emulsion that you can do this in a particle accelerator, or you can bring some emulsion to a space. So charged particles, cosmic rays, will heal that emulsion, or you will expose it in a particle accelerator. You can have different tracks, and you can see the tracks are quite different. What is the difference between all these tracks? Okay, the LET, yes, but look at this, what happened here?
The particles are different.
Size of
The element, the charge, the mass. So depending on the mass, the energy, you have different distribution of events through the track. So example, you have a helium here, proton, and you can have an iron beam. Look at the density of ionization events on the tracks. And to have a perspective, this is a kind of drawing of a cell to be on a scale. Okay? So imagine if we can visualize these tracks in a nucleus of the cells in some way or another, right? Well, we can. So it's not a perfect match, but now we can see this magical interaction between the physics, the ionization event, and an actual biology system. Okay, and GammaH2AX allow you to do that, plus other markers and other proteins that you can use. But basically, you can have a kind of mechanistic explanation of what's going on between a track with certain speed, velocity, charge, mass, and what happened at the DNA level. This, to me, is fascinating. And the story about this is, why it's interesting to me was because, you know, astronauts went to space and started seeing light flashes. You know, like lights or explosions in the eye when they try to go to sleep. And one of the theories was that cosmic rays, those charged particles, going through the brain, through the eyes, and produce those interactions at, we don't know yet where, but in some cells in the retina of the brain produce a signal that triggers something in the eye and the brain. And basically what happened is something related with one track of this, a nuclear event or cytoplasmic event. We don't know. And the point is, why we don't know? Because imagine the brain. How we can probe these interactions irradiated to a broad beam, a brain, in a petri dish if you can, with an explant or neural culture in a broad beam, quite different, very difficult to do this, right? So the only way just to relate one track, cell, single events, a very simple marker of DNA damage or signal of repair, we have it, but you can correlate with certain functional parameters using a microbeam. So that's the reason what is important of microbeams in respect to the broad beam. This is one of the examples. So you can have a big picture, you go to space, you get irradiated, you get a signal, but where the hell happened at the cellular level or the molecular level? So that's the reason you need to work with a combination of broad beam to attack some of the problems. But if you want to understand, if you're lucky, very small scale problems, maybe you need a microbeam, okay? And this is a kind of, just to make sure that we understand this. Remember when we were talking about LET, the concept of dose, particle fluence, remember that? Some people, when we're talking about high altitude radiation or particle radiation biology, the concept of dose, apple and oranges, you know, it's good to know it, but maybe have nothing to do with reality. And reality is more or less expressed in this way. We have here an example, a volume of tissue or cell exposed to low altitude radiation, gamma rays. And this is kind of the way that the photons are distributed in the volume. Let's do GammaH2AX. This is the nuclei. So you can see the LET expression on the biology level. Tracks in this homogeneous distribution all around the place. Okay? Charged particle, because of high altitude radiation. A little different, don't you think? And actually it's not realistic, because as Charles said, you remember Charles saw some little dots in the cells surrounding a big dot? Okay, this is a representation of a track of heavy ion, high altitude radiation go through a volume, but here is not represented the delta rays of the penumbra. A few tracks that will come out from this core of the track. Anyway, if you do the trick, horizontal irradiation, in some way, you can see this. And these are tracks on cells. An interesting thing too is that if you irradiate this way, one track can irradiate multiple cells, depending on the energy, the penetration. So when we're talking about low dose or low frequency or low fluences, the concept of dose is kind of just tricky. We will not describe what is going on at the cell level. So, okay, the same dose unit, let's assume this is the same dose unit for low LT, high LT, the distribution of the energy, the position of the events are completely different, okay? And the probability of some of the events occurred are different too. So this is a completely different universe here that we need to think about. Well, this is the beautiful microbeam experiment. There you can see what can be done. The beauty of have a cell right there waiting for you, hit me, okay? So you can manipulate, you can move the cell around, you can do a lot of things that you need to, yeah, again, to me it's an art doing this. So doing this kind of experiments is absolutely beauty and require a lot of training, interest and passion for this. And you can understand a lot of things. But never forget the big scale too, okay? This is a single cell or a few cells in a monolayer. But when you go to risk assessment or understand big problems, you need to keep a little in perspective what we're talking about. And something that Brian will talk about and Sally will talk about this. But in order to understand this very simple question, this is wonderful, how this problem, okay? What we say today, this is a kind of one of my experiments, very early experiment, very bad GammaH2AX when we just started. And this is, I think it's 1 GeV, or no, iron, 600 MeV, high energy, okay? And you can see the production of tracks, and this is a dose, control, 0.5 gray, 1 gray, 2 gray. Look at this. This is tremendous amount of the particle. But again, look at this. Tracks can hit several cells at the same time. We're talking about three-dimensional element. Okay? When we're talking about monolayers of cell microbeam, never occurs. But remember bystander effect. It's always something there. And this is kind of this is a very low fluence and 1 GeV ions. Look at this, one track hitting several cells. And you can see this little dot around here. Guess what it is? Tracks, maybe tracks, delta rays. Maybe some bystander effect right there too. These are NT2 cells, neural stem cells. So they are dividing undifferentiated cells. They're easy to work with. So kind of pretty standard in terms of how to handle these cells. But I'm interested in the other extreme, in neurons, fully differentiated cells that they're a little more tricky to handle. So we apply the same techniques to see what is the response of neurons in culture to 1 GeV iron expression of DNA damage and using GammaH2AX. So again, the same thing. They have the kinetics are a little different, the dose response are a little different, but you can see the effect of this track using the same probe in very complex system, like a neurons in culture. You can see a bunch of neurons communicating with each other, axons, dendrites, and very, very active and transfer the information. That's really complicated and beautiful, but it's not so simple as a single cell with certain distance between cells or what tissue. So, and Charles mentioned one of the key issues, and guys kind of very good on this, is how to measure foci. Okay, it's not so trivial. When we start, okay, you can see the pictures, and if you put some effort, but maybe you can count foci, or it would run hundreds of pictures, and maybe you can have an idea, but it's quite different. And again, what happened is that if you have a two-dimensional image, it don't tell you much, or give you a partial idea what's going on. So as Charles said, one of the best option is to get sections of cells of the nuclei in which you can see actually the track going through the nuclei. Remember, one of the problems with any technique is background. So you can see background in all of the cells that you will use. So one of the more important things when you do this type of analysis, see what is the baseline of your cell in terms of the expression of this protein. Should be very low if your cells are happy, okay? But it's not. You will deal with some kind of background that you will need some kind of software or some imaging system that will improve your output. But basically, if you have this software with a good microscope in which you can track horizontal or vertical, in this case these are tracks, so horizontal irradiated of foci directly in this direction. You can see the foci here. You get images, you have stacks, and you can hit a reconstruction of this nuclei, and you can see the tracks in more complexly. So for example, this is a control. This is beautiful, no tracks, very happy. 100 centigrade. You get the tracks of the foci, but if you reconstruct, you can see the density of the events. You can make a lot of measurements, and Guy can tell you a lot about this. But you can quantify. If you have the parameter sets, you have your baseline and your background set, you can do a lot of quantitative analysis of this, and this is the beauty of it. This is a kind of full dose response curve and two cell lines. This is a neural stem cell, and this is a fully differentiated neuron. So you can do analysis in two different cell types. What is as a function of dose induction, and you can see very clearly how that responds. Okay, you can do also kinetics, repair, the same thing versus time, and you can see how the decrease of what is that kinetic. So we usually, I think I have the data here. This is this. What is this? Okay, the first is kinetics, and you can see the different dose of radiation with times, and this is foci per cell, and you can see the dose has a peak around half an hour. I'm going to generally assume that 20 minutes, 30 minutes are kind of where you will find a peak. There are variations, of course, between cells, but 20 minutes, 30 minutes are kind of the magic number as far as I know. It's kind of like that, Charles? Okay. This is the dose. No, this is time. Okay, I'm sorry. This is for stem cells, and this is for neural cells. You can see some changes in the kinetics. The repair is a little different. We are talking about undifferentiated cells versus fully differentiated neural cells. There is some changes in the repair capabilities too. So this is a thing that you can do. And that's just to give you an idea what an exercise will be. We did this at Brookhaven. We do a GammaH2AX experiment using this energy of iron ions. This is the LET of the particle. And we try to simulate, use the Charles formula, try to find out what are the correlation between fluences and doses, and try to compare what happens. So we want to have some frequencies of hits less than a particle, one particle, and more than 6 particles, for example. So you calculate the dose to get that, depending on the LET, the size of the nuclei, and you come up with this dose in centigrade when you give the fluence and the unhit fraction and the hit fraction. So you can have an idea what are the cells, the amount of cells that will be hit or not, and the average hits per cell. Nice numbers. And this is the way they irradiate, horizontal, and this is what they're doing in broad beam. We are not interested in that. This is a kind of standard protocol for GammaH2AX. You can refine, depending if you're using tissue, depending on the antibody. So it's a broad, the small detail for each of the protocol that you will use. Okay, this is control, less than 1 hit per cell, as a control, nothing. This is 8 centigrade, so 1 GeV ion, less than 1 hit per cell. This is the horizontal irradiation, and this is the vertical. Can you see the frequency? Do you see that? A horizontal, look at the tracks numbers, look at the vertical foci. This is 16 centigrade, 1 hit per cell, more or less. Horizontal, well, look at this. It's not perfect. It's not a perfect 1 hit. You have a distribution, a probability of a hit. But it gives us an idea how you can correlate these hit frequencies with doses. This is 100 centigrade, more than a hit per cell. quite clear. And this kind of representation of each of the doses on tracks and foci. Okay, and you know, this is the result at the end. So what the dose, the predicted heat fraction, and actually what we observe. We measured that, and this is the approximation. It's not so good, but it's close. Okay, so you can do very good calculation if your software is good, you have a good image system and good analysis, you can have a very nice correlation what is heat at the end. Okay, and what are the limitations of the techniques? Well, so we're talking about the GammaH2AX represent repair and double strand breaks. Well, sometimes it's not. Replication also can produce an expression of this protein, this GammaH2AX. Again, we know that it's an indirect representation, a direct representation of double strand breaks. And sometimes the timing in which the foci disappear, doesn't matter if it's broad, beam, microbeam, sometimes it's not matched perfectly what the induction or repair of double strand breaks. So there's a kind of limitations that you need to take into account. It's a great technique. It's very powerful if you handle correctly, if you have the right technology to do that, but they have some pitfalls. But it's a good system, and currently it's a good biodosimeter for radiation effects and, you know, exposure to radiation. So it's wonderful, but be aware there is some limitations for this. Okay.